Let's continue the ZAERO Advanced Training, Section 3, Open Loop ASE Analysis. So we'll look at the bulk data cards here for the open loop ASE design. The open loop ASE model can be either without the actuator input and sensor output, which gives the Aeroelastic model, or with the actuator input and sensor output, which gives the plant model, but without the control system. The stability boundary of the Aeroelastic model and the plant model is the same, since the stability boundary of the linear system is independent of the input and output. So our bulk data cards, here we have the ACTU to define the actuator. The AEROLAG card defines the approximation lag routes and is required for the state space approach. The APCNSND and APCNSCP are approximation constraints, and the APCONST card is also for approximation constraints. The ASE card is the main card which calls out to all of the other cards, so this defines the ASE system. The ASE controller, ASECONT, defines basic parameters of the control system. ASEOUT allows you to export the plant models for further analysis in other software packages such as MATLAB. The ASESNSR or the updated ASESNS1 define the sensors. We'll skip D in it, it's not important. Grid FSET allows you to define a set of forces applied at structural grid points. The MinIMP1 or MinIMP1 cards allow you to replace coefficients in the rigid body submatrices of the RFA by the user-supplied aerodynamic stability derivatives. The MINSTAT card defines parameters for the aerodynamic approximation, or the RFA. The RBRED, or rigid body reduction, defines rigid body modes for enforcement of zero eigenvalues. The SENSET card allows you to define a set of sensors. The SURFSET card defines a set of control surfaces. And then finally, the PLTMIST allows you to generate files for plotting the comparison of the RFA to the GAFs. This is the bulk data interrelationship for open loop ASE analysis. So as I said, the ASE card is the main card where everything flows out of. So our case control section will list a subcase and then ASE equals. This ASE refers to the ASE bulk data card. Then the ASEOUT allows you to export the plant models. Then we have the fields of the ASE card call out to the other ASE bulk data cards, which then can further refer to more bulk data cards. So let's look at the ASE card. This defines the Aeroservoelasticity analysis and refers to the bulk data cards that define the specific analysis parameters. So our SID is the set identification number referred to from the case control command. Con ID refers to an ASE controller card to specify parameters of the control system. FLT ID refers to the Flutter bulk data card, which define all of the analysis flight conditions. The states field refers to the MLDSTAT card to define parameters for the airframe states. RAA ID refers to a MINSTAT card to specify parameters for the RFA. And RAA ID can be 0, in which case the frequency domain approach is used. And then MARID refers to a C margin card to specify parameters for the control margin analysis. And this is for a closed loop analysis, which we'll talk about in a later section. And the remark 3 here is important. The units of mass and length involved in the ASE analysis are defined by FTM unit and FTL unit, which are specified in the fixed cards, and these are referred to as the analysis units, which can be different than the model units. Remember, the model units are specified in the AeroZ bulk data card. The MLDSTAT card transforms the rigid body modes to the airframe states, which we'll look at later. Okay, the next card is the ASECONT, or the controller card. So this defines parameters for the plant model and the closed loop system. So we have the SID field, to define an ID number. SURF ID refers to a SURFSET and or grid FSET cards to define the control surfaces or grid forces. SENS ID refers to the SENSET bulk data card, which lists out the ASE sensors. TF ID, the remaining fields are for closed loop systems. TF ID refers to the TF set card to specify the control transfer functions. Gain ID refers to the gain set card to list out the ASE gain cards. CONCT ID field refers to the CNCT set card, which lists out the fixed connections. And then EINP ID and EOUT ID refer to set 1 cards, which list out the external input and external output bulk data cards. And as I said, for closed loop, the TF ID, gain ID, and CONCT ID can be 0 or blank, which means you can just use the the field SURF ID and SENS ID to define the outputs and inputs of the plant model. Okay, next we have the SURFSET bulk data card, which simply lists out the ID numbers of your control surfaces. So the SURF fields can refer to the AESURFZ, AESLink, PZT mode, or JetForce bulk data cards. And the grid FSET lists out the ID numbers of the grid force bulk data cards. The ACTU is the actuator transfer function card. So we have an ID number, and then we have A0, A1, and A2, which define the parameters shown here in the transfer function of the actuator. So note that we have A0 in the numerator and denominator here, so that the DC gain of this actuator is always 1. That's enforced just by the way the card is defined, and then you'll note it's a third order transfer function. So all of the ID numbers, the first field ID of the actuator, sensors, CJunct, MIMO SS, and CISO TF cards must be unique. And the actuators are referred to by the AESURFZ, the AESLink, the PZT mode, or the JetForce bulk data cards. Now, if you have a higher order actuator that you would like to model, then you must split it up into two transfer functions, one of this form and then a second transfer function that you connect in series to this transfer function. And you can define that using a CISO TF bulk data card so that you have a higher order transfer function defined. Now A0, A1, and A2 can be blank if you don't know your actuator transfer function. In that case, ZAERO will use the equations here. So omega max is the frequency of the highest normal mode used in the analysis. So then A0 is set to 27 times omega max cubed. A1 is 13.5 times omega max squared, and then A2 is 4.5 times omega max. So these values will create an actuator with dynamics that are much higher than the highest natural frequency of your normal mode analysis. Therefore, this actuator does not influence the dynamics of the ASE system that much. So note that we do have a restriction on the type of transfer function that you can define, and it also is a third order transfer function. So the question arises, what if your actual actuator is only first order? And this is a question that a customer had sent us. So for example, let's say you have a first order transfer function, which is 40.84 over S plus 40.84. Now, if you try to define the ZAERO actuator with A0 is 40.84, A1 is 1, and then A2 is 0, that results in this transfer function here, which is incorrect. So if we go look at the Bode diagram, the desired is the blue, and then this equation, the incorrect transfer function, is shown in red. And you can see that these two are not similar at all. In particular, if we come out to 10 hertz, you can see that the desired actuator is starting to be attenuated at 10 Hertz, but not too much. But the incorrect actuator, we're already at minus 70 dB, so it's practically zero. If we look at 1 Hertz, the desired actuator has no attenuation. The incorrect actuator is about minus 20 dB. So once again, that's significant attenuation, so that's incorrect. So the solution here, what we can do is factor the ZAERO default actuator, where omega max is the highest natural frequency. So if we take that equation, we can factor it into these two transfer functions. So we have a first order and a second order transfer function. Now what we're going to do is take the second order portion, this transfer function, and combine it with the first order desired actuator, which we have up here. So that gives us this transfer function now. So if we take omega max to be 40 Hertz, which is 251.3 radians per second, then the third order actuator transfer function is shown by this equation here. So we've plotted that in yellow on the plot at the right. So if we go out to 40 Hertz, which is the maximum frequency present in our model, 10, 20, 30, 40, you can see that up to 40 Hertz, the desired actuator blue and the final actuator yellow, which we've defined, are practically the same in magnitude and phase. And then, of course, out past 40 Hertz, we have additional dynamics, but we don't really care out past 40 Hertz because that's the maximum frequency we have in the structure. So this is what you would do. In the same fashion, if you had a second order actuator, you could take the first order transfer function here and combine it with your second order actuator to get your final third order actuator. Okay, next we have the SENSET card, which lists out the ID numbers of the ASE sensors, which brings us to the ASE sensor card. So the ASE sensor is the original ASE sensor card. For new input decks that you're defining, we recommend using the ASE Sense 1. So the ASE sensor is here for reference, but let's go ahead and move on to the ASE Sense 1 because it's much easier to read. Well, we can make a comparison here. If we look at the example here, this is an acceleration sensor. So we have the ID number, and then we have the label and I key to define the sensor. So the grid GT3 means this is a grid sensor. G is acceleration, and then T3 is the direction. So we have a vertical acceleration sensor at grid number 7. If we go back to the ASE sensor definition, we have a type here, which is a number, and then we have SGID, which is the grid ID, and then SC component number. So at the type 2, we have to look in the table and look up what does type 2 mean. And if we come down here to the table in the user's manual, we can see that type 2 means acceleration at a structural degree of freedom. And then we have to go to the SC field, and we see that the component number is 6. So that is rotation about the z-axis. So we have a rotational acceleration sensor about the z-axis at grid number 7. So you can see that the ASE sensor card is much harder to decipher. You have to refer to the user's manual to see what does this type field mean. So you can see that we have displacement, velocity, acceleration sensors. Then we can include control surface and so forth and so on. But the type number, you can see it's just a code to look up to see what kind of sensor type it is. So let's move back to the ASE Sensor 1 card, where instead of the type and SC fields, we just have the label, which is an ASCII string, which is self-descriptive. So if we go through the different types of sensors that we have available, we have modal X, modal V, and modal G, which allow you to measure the generalized modal coordinates. So this can either be the coordinate itself, the velocity, or acceleration. And then next we have the grid sensors. So grid xt1, grid xt2, grid xt3. This is displacement along the x, y, and z directions. And then grid xr is rotation. Then we move on to the grid v. So the grid v is the time derivative of the displacement of the grid. So we have t1, t2, t3, and then r1, r2, r3. And then we have grid g, which is the second derivative with respect to time. And then next we have accelerometers. So accel t1, accel t2, and accel t3. The difference between the accelerometer and the grid GT is the phugoid mode term, which is described in the MINSTAT bulk data card. So we'll see that later. But basically, if you have accelerometers, use the accel option. But just know that if you do not have a phugoid mode defined in your MINSTAT card, then the accel and the grid GT are identical. Next, we have the force options. So we can measure the force along the x, y, or z direction, or the moment about a rotational degree of freedom. We can also take the time derivative of the force. So we have force t, and we have our force v, and then force g for the first derivative and second derivative with respect to time. Next, we can use component loads as a sensor. So we have a load mod. This refers to a load mod card. So you can measure component loads, for example, wing root bending or wing shear. You can also take the first or second time derivative of the load mod result. Next, we have the DMI, which allows you to have a generic parameter in terms of modal values imported by the DMI bulk data card. So for example, in Nastran, you can have modal stress or modal strain. So you can output those quantities by the DMI output in Nastran, and then you can import that into ZAERO to directly measure modal stress or modal strain. Then we have the delta, X, V, and G. This is control surface deflection. So this measures the actual control surface deflection, velocity, or acceleration. Then we have the CP, which is a pressure coefficient on an aerodynamic box. So I key there is the identification number of the aerodynamic box. Then we have CNTL, X, V, and G. So CNTL X is the same as the grid X, except it also includes control surface deflection effect if the grid point is on a control surface. So if you have an accelerometer that's sitting out on a control surface, then you would want to use CNTL G T3, for example, if it's in the Z direction. So this will pick up the acceleration of that grid point due to both modal coordinates and control surface deflection. For the most part, I would imagine that you don't have sensors out on the control surfaces though, so you don't need to use that. But if you do, just be aware of that. If you want to pick up the control rotation of that control surface, then you need to use the CNTL option. Okay, so remarks here. We have some important remarks. Remark 3, if the MLDSTAT card is used to replace the rigid body states with airframe states, then the modal X, modal V, and modal G options still return the rigid body states rather than the airframe states. So if you want to measure the airframe states alpha, beta, W, or V, it's recommended to compute them from the rigid body states TZ dot, RY, TY dot, and RZ, where alpha is equal to minus TZ dot over V, and then we're adding in RY. W is equal to minus TZ dot plus V times RY. beta is equal to ty dot over v plus rz, and v is ty dot plus v times rz. So an example is shown here to calculate alpha, assuming we have support equals 3.5 in the assign FEM statement, and the airspeed varies from 50 to 200. So if you have an angle of attack sensor on your aircraft and you'd like to reproduce that in ZAERO, and you're using the MLDSTAT card, you can do it this way. So first we have sensor 101, which measures TZ dot. So that's a modal V. I key is 1, which means our first modal state. We have support is 3.5, so our first modal state is the z direction, and then modal v means the velocity, so that's tz dot. Sensor 102 here measures ry, so ry is the second modal coordinates, and then we use modal x to directly measure ry. Now we use an ASE gain card, which multiplies tz dot by 1 over v. Because if we look back at our equation here, remember alpha is minus tz dot over v infinity. So this ASE gain card, let's see, takes ASE sensor 101, the first output component of that, and then we're feeding into a C-junct card, which will measure alpha, and then we're multiplying the gain value. It's not a fixed gain, but it's a table lookup gain, and the type here is based on velocity. Now, the way we can get to multiply 1 over v is in the table D1 card, we can use x-axis log and y-axis log, and this will give us an exact interpolation for f of v is 1 over v. So we take, let's see, x-axis is log, y-axis is log. We set extrapolation to no, our factor is 1. Now when our x is 50, or when v is 50, then 1 over v is 0.02. When x is 200, then 1 over 200 is 0.005. And now because our axis types are logs, when we do linear interpolation on these values, but then we do the log before and after the lookup, we get an exact lookup for f of v equals 1 over v. So what we've accomplished here by using this ASE gain card is we're taking the ASE sensor, which is measuring tz dot, multiplying it by 1 over v, so that will give us this alpha parameter here. Now we take the C-junct. It's got 2 inputs and 1 output. Our other input is, let's see, a connection to 102. That's the RY. TZ dot divided by V, that's from our table. And then the C-junct has a minus sign here, so that's the negative sign you see in the alpha. And then we're adding in RY. So that's the final output of this C-junct is alpha measured in radians. So this method that's described here can be used whether or not the MLDSTAT card is used to replace the rigid body states with the airframe states. Next, remark 4, usually the accelerometer readings, and I mentioned this on the last slide, but usually accelerometer readings are identical to the second time derivatives, which are the accelerations. But in the case when the MIN-IMP1 card is used with the phugoid mode option activated to account for accelerations due to gravity, these should be taken out of the accelerometer readings to be consistent with the flight dynamics. So for this, the label Excel can be used to indicate an accelerometer reading. Next, we have the ASEOUT card to export the state space ASE matrices. So we have an ID number, which doesn't matter. Next, we have the ID ASE. This refers to an ASE, G-loads, or M-loads bulk data cards. Next is the index. So this is the index of a selected velocity density pair resulting from the altitude list from the XMATM card, or the VI row I from the fix Mach, or V in the fix M den. So for the altitude, index equals 1 refers to the last or the highest altitude, whereas in the fix Mach and fix M den, index 1 refers to the first VI row I, or the first VI list. The reason for this is in the fix MATM, you specify altitudes from low to high. However, when you look at it in terms of dynamic pressure, that's actually high to low. So the fix MATM card is backwards. So the index here for the fix MATM, index 1 would be the last altitude because that's the lowest dynamic pressure. Next is the level. This is the requested Aeroservoelastic matrices. So we either can choose AE model, plant, vehicle, or closed system. And usually when I use this model, I choose the plant option because using the plant gives you the open loop model, but it gives you the control surface, the actuators, and the sensors, input and output, which is normally what you need for control system design. Next, the ID FREQ field activates the frequency response function option. So this refers to a frequency or frequency 1 bulk data card. If ID FREQ is blank, then the ASEOUT card outputs a state space model. However, if it refers to one of these cards, then it outputs the FRF. And this is only available for the frequency domain ASE M-loads or G-loads analysis. Next, we have the file name, which is just the name of the file. And like all file name options, we have the $sign option. So if your file name is longer than 16 characters, then you can refer to an ext file, a bulk data card for a file name up to 56 characters long. And then lastly, we have the format of the file. So the form is a character string, either format or format 23. So format 23 just gives you more digits in case you'd like full double precision output. Next is the rigid body reduction card to enforce 0 eigenvalues for the rigid body modes. So this defines the rigid body modes for enforcement of 0 eigenvalues for the state space system matrix, and this is inactive for the frequency domain approach. So we have an ID number, and then we have the ID ASE, which refers to an ASE, M-loads, E-loads, G-loads, DFS, or nonlinear flutter card for which the state space approach is employed. C is the component numbers of the rigid body directions. These component numbers correspond to the remaining rigid body modes after the deletion of modes by the M-list entry in the flutter card. Next, we have GID, which is a reference structural grid point for which the rigid body mode displacements can be extracted. GID can be blank if your support entry in assign FEM has the / integer option where you specify a grid. So usually I recommend in the support option of assign FEM, if for example a full span model, you'd have support equals -1, 2, 3, 4, 5, 6, and then / and then a reference grid point. So if that reference grid point is in your assign FEM, then GID can be blank. And then lastly, we have the Fugo option, which is a character string either yes or no. For no, then the columns in A0, A1, and E corresponding to the 4 aft rigid body motion are replaced by zeros. If Fugo equals yes, then only the column in A0 is replaced by zeros. Let's see if there's anything important we missed. Let's go to remark 5 here. So the column in the A1 matrix contains the aerodynamic stability derivatives associated with drag. It's often the case that the Fugoid mode is unstable, which may introduce divergent motion in the time domain analysis. In this case, it's desired to remove the Fugoid mode in the equation by specifying Fugo equals no. On the other hand, if the user intends to include the phugoid mode effects, it's recommended that the aerodynamic stability derivatives associated with drag be imported into the A1 matrix using the MinIMP1 card, and then specify phugo equals yes. Next, we have the MINSTAT card, which is parameters for the rational aerodynamic approximation. So our SID is the identification number referred to by the ASE card. Lag ID refers to an AEROLAG card, which specifies approximation routes for the generalized time matrices due to structural modes and control surface kinematic modes. Now, lag ID can be blank, in which case you have no aerodynamic lag states, but we don't recommend that. We would recommend always having aerodynamic lag states. IT max is the number of DED iterations. So if IT max is 0, that triggers Rogers approximation to be used, and if IT max is greater than 0, then the modified minimum state approximation is used. And if you are wanting to match results from older versions of ZAERO, where you have Karpel's minimum state approximation, that can be triggered by using IT max less than 0. APCID refers to an APCONST or APCNSND cards, which specify approximation constraints. The P-weight generally is not needed, so you can ignore that field. The DMAT ID refers to the DINIT card, which once again, that you don't need to use that. That's rarely, if ever, needed. KList refers to set 1 or set add cards, which contain a list of reduced frequency indices. These are excluded from the rational aerodynamic approximation. So in your MK-AeroZ card, if you have a lot of reduced frequencies defined and for whatever reason you don't want all of those reduced frequencies to be used in the rational function approximation, you can exclude some of those reduced frequencies using the KList option. Next, we have the MinIMP field, which refers to the MinIMP1 card, which allows the user to replace elements in the RFA matrices by user-supplied values. So remember that first, the RFA is performed ignoring the MinIMP1 card, and then after the RFA results are obtained, then the MinIMP1 card is applied, and those elements in the A0, A1, and A2 matrices are simply updated with the values supplied by the MinIMP1 card. Next, we have a print option, which allows you to print out the matrices on the output file. So if print is 0, there's no print out, and generally there's not. If you do want your plant matrix output, I would recommend using the ASEOUT card. However, the difference there is the ASEOUT only outputs the A matrix. If you actually want to know what the A0, A1, A2, D, R, and E matrices are, then you have to use the print option in the MinStat card. The save option allows you to save or retrieve approximation data. I would recommend not using the save option because the approximation is computed very quickly in ZAERO, so there's not much time saving by saving and then acquiring your approximation for later analyses. The exception would be is if you're doing hundreds and hundreds of analyses where you already know that the RFA is going to be identical for all of them, then the small time savings may be worth it. But in general, trying to save and acquire the RFA data, you may forget that you're doing that. You'll change some parameters and then not see a difference in your results because ZAERO won't print a warning if you change some approximation parameters and then you acquire results from older approximation parameters. So in general, I would recommend not using this option, but it is available if you want it. Next, we have the MS mod field. So if MS mod is greater than 0, then Karpel's minimum state approximation is used. Oh, I misspoke earlier. That was right. That's for an older version of ZAERO. I said that if IT max was less than 0, then Karpel's minimum state is used. That is incorrect. IT max must be 0 or greater than 0. To trigger the old Karpel's minimum state method, then you use the MS-mod field. The default here is 0, which means use the Zona recommended minimum state approximation method. So that's the modified minimum state approximation. If, however, when MS-mod is equal to 1, then Karpel's minimum state approximation method is used. Lastly, actually, we'll discuss lag IDG and DMAT IDG when we go over gust, because those are just specific to the gust. And we don't need to go over any of these. Okay, next is the AEROLAG card. So this defines the approximation routes for the RFA. So we have an ID number. Next is NLAG, which is the number of approximation lag terms. And then the RI, so R1, R2, R3, and so on. This is open-ended. This is the NLAG distinct root values. The SID is referred to by the MINSTAT card. And so usually you can leave the RI values blank and only specify NLAG. So if R1 is blank, then the approximation root values are calculated by this equation, where Kmax here is the maximum reduced frequency of the maximum reduced frequency in the MK-AeroZ card. So usually that is sufficient. You can let ZAERO calculate the root values for you, and you only modify NLAG, the actual number of lag terms, until you find a good approximation. However, occasionally you may find that by modifying NLAG only, you cannot get good approximation results. And this may be the case if you have reduced frequencies defined that are much less than 1 or much greater than 1. So if you're doing a gust analysis and your reduced frequency goes up to 5 or 10, this equation may not give you the best lag state values. So in this case, what I've found that works is I can calculate my own aerodynamic lag root values by substituting 1 in for Kmax into this equation. So I use this equation myself. I take my NLAG that I specify in field 3, substitute it into the equation, and then plug in I equals 1, 2, 3, 4, and so on up to NLAG to get my NLAG number of root values. Then take those values that I calculate using substituting 1 in for Kmax and specify those values in R1, R2, R3, and so on. So in that way, you may get better approximation. But as I said, only try this after trying the default values if you find that the default values don't work. Next, we have the APCONST, which allows you to define approximation constraints. So we have the ID number. Next, DA0 defines the default steady fit constraint. When DA0 equals 0, then there's no constraint. When DA0 equals 1, then we match the data at K1 equals 0. Next is the DA1 field. This defines the default constraint on the imaginary part. When DA1 is less than 0, then there's no constraint. If DA1 equals 0, then we set A1 equals to 0. If DA1 equals 1, then we match the imaginary part of the data for Kmax. And if DA1 is greater than 1, then we match the imaginary part of the data at that particular K value. So for example, if DA1 is 3, then we'd match the imaginary part of the data at K3, the third reduced frequency value. Next, DA2 defines the default constraint on the real part. So when DA2 is less than 0, there's no constraint. For DA2 equals 0, then we set A2 equals 0. For DA2 equals 1, then we match the real part of the data at Kmax. And when DA2 is greater than 1, then we match the real part of the data at that KDA2. And then next, the NRP, NCP, FR, and FC allow us to partition the approximation matrices. So NRP is the number of row partitions to assign non-default constraints, and NCP is the number of column partitions to define non-default constraints. And then our FR is the index of the first row of the ith row partition. So if NRP equals, for example, 5, then you would have 5 FR values. And these are the index of the first row of each of those 5 partitions. And then FC of J is the index of the first column of the jth column partition. So for example, if NCP was 3, you would have 3 FC values in the card. So the size of the generalized aerodynamic force matrix Q is the number of modes plus the number of component load modes by the number of modes plus the number of control surfaces plus the number of gust modes. The default constraint definitions, we have some options here. So if DA0 equals 1, this defines the steady fit constraint, where the data match constraint is at the first reduced frequency K1 equals 0. So this means Q tilde of K1 equals Q of K1. For DA1 equals 0, this defines the approximation slope constraint A1 equals 0, where A1 is the aerodynamic damping matrix in the approximation formula. And a default constraint of DA1 equals 1 defines the imaginary part data match constraint at K equals K max. And for DA1 equals G, this defines the imaginary part of the data match constraint K equals KG, which gives us this constraint. And then similarly, DA2 is for the on the A2 matrix. So for applying the RFA for gust, we highly recommend DA2 equals 0, but only on the gust columns. The default constraint DA2 equals 1 defines the real part data match constraint K equals K max. And then when DA2 equals F, that defines this constraint. The default constraints are applied to all terms of the aerodynamic matrix, whether or not non-default constraints are defined in the APCNSND cards. And application of the non-default constraints to the definite terms of the aerodynamic matrix requires that one specify these terms via partitioning of the aerodynamic matrix into blocks. And the partitioning is defined in this card by specifying the number of row and column partitions, as well as the indices of the first elements of these blocks. We recommend DA0 equal 1 for all aerodynamic terms, and DA1 is -1, DA2 is -1, usually yield the best results. And we note here that DA1 equals 1 can cause large modeling errors. So here are two examples of the definitions of default constraints. So this first one here is our what we recommend generally. So DA0 is 1. DA1 and DA2 are both -1, so no constraints for them. And then secondly, just as an option or illustration here, we have all aerodynamic terms are constrained at K equals 0 and K equals K max. So in this case, DA0 is 1, DA1 is 1, and DA2 is 1. But this one we generally wouldn't recommend. This is just an example. The non-default constraints are defined in the APCNSND card with the same identification number as that of the APCONST card. So the APCNSND are the non-default constraints. So we have an ID number, and then the IP and JP are indices of the block, which assumes the non-default constraints, and PA0, PA1, and PA2 are the parameters to override the default constraints DA0, DA1, and DA2 defined in the APCONST card. The meaning of these parameters is the same as that of the APCONST. It just gives different constraints for this particular block. So this card is referred to by the APCONST by having the ID number the same as the APCONST. So the MINSTAT card will refer to an APCONST card with some given ID, and then the APCNSND will have that same ID number as the APCONST. So here's an example. So this aerodynamic matrix contains 7 structural modes and 1 gust mode. All of the columns are constrained at the first reduced frequency, K1 equals 0, and then an additional approximation constraint, PA2 equals 0, is defined for the gust column. So when you do have gust columns present, we would always recommend doing this. So the APCONST card, our default constraints are the recommended DA0 is 1, DA1 is -1, DA2 is -1. We only have 1 row partition because we don't want to modify anything there, but the number of column partitions, we have 2. So we have 7 structural modes and no control surface modes, which means the gust mode is column number 8. So the row partition, that has to be 1 for the first one, and then because there's only 1 row partition, we move to FC. And we have 2 column partitions. So FC1 is 1, and then FC2 is 8. So the second column partition is the gust column partition. So now the APCNSND, note that the ID number 41 is the same as the APCONST. The IPJP tell us which row and column partition this is. So IP is 1 because there's only 1 row partition, and JP is 2, specifying the second column partition. Now our PA0 is 1, PA1 is -1, and then PA2 is 0, because for the gust column, we recommend A2 to be 0. And this is just another example. We don't necessarily recommend using these values, but here we have 3 column partitions. So the second column partition starts at 3, and then the last column partition is 8. So in this example, actually what's going on here, this could be useful. We've split up the rigid body modes and the elastic modes. So the first 2 modes are rigid body modes, and then so modes 3 through 7 are elastic modes. So our default constraints are going to end up being applied to the elastic modes. And then note here, IP1 and JP1, so this is the first column partition, and our first column partition contains columns 1 and 2, which are the rigid body modes. So here we have this additional constraint, PA1, 2. So we're matching the first non-zero reduced frequency. We're matching. So what we're trying to do here is match the stability derivatives. So this could be a useful tool to use. And then graphically here we've shown how we can partition this up. So we have 7 structure modes. Now we have 2 control modes and 2 gust modes. So we've got 7 plus 2 is 9, plus 2 is 11. So we have a total of 11 columns. And then we've got 7 structure modes and 5 component loads. So we have 12 rows. And this is similar to our last example, where we've got the first column partition, which contains, let's see, our rigid body modes. So we have the restriction PA1 is 2. And then for our elastic modes, we've got A01, A1 is 1, and A2 is 1. And then on our gust columns, we have A0 is 1, A1 is -1, and A2 is 0. Next, we have the APCNSCP, which is approximation constraints for the unsteady CP. Now, the approximation constraints that we defined previously on the APCONST card and APCNSND, those will also apply to the CP constraints. However, if you want to, for whatever reason, apply different approximation constraints on your CP, you can do that using this card. But usually, the APCNSCP is not needed. So once again, the definitions here are all the same as before on the APCONST, except now we're applying constraints onto the unsteady CP. Now, where is this actually used? For the component loads, if you use the SOF option equals yes, ZAERO will compute your component loads by integrating the loads on the aerodynamic boxes, which does take more time. In that case, we need the RFA applied at the box level of the model instead of on the modes. So in that case, we do perform the rational function approximation directly on the boxes, and that is where this approximation constraints on the CP comes in. If you do not make use of the SOF option, then the approximation on the CP is not used. And this is showing in the same way on the APCONST card how we split up the column partitions. It's the same way here for the CP, except now the rows is not modes, it's the directly on each panel. So if you have 1,000 panels on your aerodynamic model, then this matrix would have 1,000 rows. Next, we have the PLTMIST card, which plots or creates data files which allow you to plot the GAF coefficients. The ID number is arbitrary. ID ASE refers to an ASE, M-loads, E-loads, G-loads, or nonlinear flutter card. I-row is the row number of the generalized aerodynamic matrix. I-column is the column number of the generalized aerodynamic matrix. K-list refers to an AE-FAT card to list out a list of reduced frequencies. Form is not used, and then file name refers to the data file name. Now, K-list can be blank, in which case the list of reduced frequencies that are used to compute the GAF data is just from the MK-AeroZ card. So in your MK-AeroZ card, if your reduced frequencies are, for example, 0, 0.1, 0.2, 0.5, and 1, then those values will be used to plug into your rational function approximation to calculate what the GAFs are on your approximated model. What I like to do is specify an AE-FAT card with a much denser list of reduced frequencies, for example, 0 to 1 in increments of 0.01. That way you'll get a much smoother curve, and you'll see what the approximation is doing for reduced frequencies in between your discrete values that are present in the MK-AeroZ card. So if we look at some plots here that was actually done, so the computed values are the tabulated values from the AIC matrix, so that's shown in the blue circles, and then the red is the approximated. So to generate these plots, we've actually have two, I believe, PLTMIST cards for the same data, so that we can see what the X's correspond to the reduced frequencies that we have the circles at. So that's the actual reduced frequencies in defined, and then the red curve is a more fine plot. So we have more reduced frequencies are used to compute this curve, and we can do that because remember when we do the RFA, it's now just a function of S. So we can plug in any reduced frequency we want. So you can see that this particular approximation gives us a smooth curve, and it matches the data pretty well. Now, usually I'll say you do not need to go to this level of detail to see how well your approximation matches the tabulated gaffs. Normally, you can just look at the flutter results, and if you get a good matching of flutter results, then you have a good approximation. But if you're curious or something's weird is going on, you can certainly use the PLTMIST card and dive down deep and look to see exactly how your approximation compares to your tabulated gaff values. Next is the MLDSTAT card for specifying airframe states. So the rigid body modes computed by the structural finite element analysis are on the principal axis, while the flight dynamic model is defined by the airframe states. And the support entry in the assign FEM executive control command transforms the rigid body mode from the principal axis to the body axis, as shown here. The MLDSTAT card further transforms the rigid body modes from the principal axis to the airframe states so that the rigid body states of the state space equation are consistent with those of the flight dynamic model. So normally in ZAERO, our rigid body modes are TX, TY, TZ, RX, RY, and RZ, but the MLDSTAT card allows us to use the airframe states instead as the rigid body modes. So now we have alpha, beta, P, Q, R, V, theta, psi. So this is achieved by the transformation matrix TA. Now for the symmetric maneuver, TA is shown here. So if we just take a look at TX, for example, TX is minus X, TX dot is minus U. The antisymmetric maneuver TA is shown here. So let's look at TY dot. This is V infinity times beta plus V infinity times psi. Now for the asymmetric maneuver, TA is a 12 by 12 matrix, which combines those two matrices. Next, we have the MinIMP1 card, which allows us to replace coefficients in the rigid body submatrices of the RFA by the user-supplied aerodynamic stability derivatives. You'll note this card looks almost identical to the RBQHH card. But remember, the RBQHH card updates the tabulated QHH, whereas the MinIMP1 replaces the terms in the RFA after the RFA is performed. So if you have this data available to you, we would recommend using both RBQHH card and the MinIMP1 card. So the A0 matrix contains the steady aerodynamic stability derivatives and the gravity terms shown here, and the A1 matrix contains the aerodynamic damping stability derivatives shown here. And all of these derivatives can be imported by the user-supplied data. Now, if you only have some of these terms, for example, you just have CL naught, CL alpha, CM alpha, but you didn't measure anything else, you can leave all of the other terms blank, and ZAERO will not modify those values. It will only use the values that you supply to update the terms in the A0 and A1 matrices. So the MinIMP1 card can be used to ensure that the rigid body responses of the ASE state space equation match that of the 6-DOF system. The following figure here is the comparison of the Bode diagrams generated by ZAERO and a flight control system model of a business jet. So the blue here is our flight control system model, and then the green is the ZAERO model. So you can see the rigid body states for, let's see, the left one here is the pitch angle, and the right one is the Z acceleration. For the rigid body portion, the two are almost identical. And then once we get out to the elastic states, of course, the 6-DOF model has no concept of what's going on elastically in the aircraft, whereas the ZAERO model has all of the dynamics due to the elastic states, which is shown up here. Without using the MinIMP1 card, the rigid body dynamics would not match. As a further example here, the aerodynamic stability derivatives of the rigid body modes computed by ZAERO are replaced by the Aero database in a flight dynamic model of a UAV. So we have two Bode diagrams with symmetric outboard flaps as input and pitch angle as output are generated and compared to the linearized Simulink model of a UAV in a classic flight dynamic theory. The ZAERO ASE model with 6 rigid body modes and no elastic modes is presented, and then we have the ZAERO ASE model with 6 rigid body modes and 24 elastic modes. And this comparison shows that the aeroelastic effects on the phugoid and short period modes are significant for this UAV. So first we have the 6 rigid body modes only on the left. The linearized Simulink model is in blue. The theory, just from equation, is green, and then the ZAERO rigid body model is red. So you can see the rigid body portion all matches pretty well. And then due to actuator dynamic effects, we get a difference out here at a higher frequency. But now when we add in the elastic modes to the ZAERO model, not only does it affect our higher frequency dynamics, it also affects the rigid body dynamics. So this shows us that there's coupling between the elastic modes and the rigid body modes, which of course cannot be captured by the Simulink model as it does not have elastic modes. So let's look at an example here. We have a cropped delta wing body configuration without an input and output, and the purpose here is to use the open loop flutter results of a cropped delta wing computed by the frequency domain approach as the reference solution, demonstrate how to apply the rational function approximation to the frequency domain, generalized aerodynamic forces for constructing state space equations using the Rogers method, and the modified minimum state method. So we have the aerodynamic model here on the left, the structure model on the right. You may recognize this as the ZAERO basic hands-on training model. And we've modified here for ASC. So we have 3 subcases: the frequency domain approach, a state space approach using Rogers method, and a state space approach using the modified minimum state method. The first subcase is the frequency domain approach. So in the ASE card, RAA ID is 0. So that signifies that we're doing frequency domain. And then ID con is 0 because we do not need an ASE controller card. So we have no control surface input and no sensors. So this is performed on the Aeroelastic system. And then the ASE card refers to the flutter card here, which defines our flight conditions as shown in the FixSum Den card. Subcase 2 is the state space approach using Rogers method. So now we have the RAA ID field referring to the MINSTAT card. In the MINSTAT card, IT max is 0. And then the lag ID refers to the AEROLAG card, where nlag equals 5. So we have 5 lag routes. And then we have an APCONST card. DA0 is 1, which imposes constraints on the RFA such that A0 equals QHH of 0. And we have 4 PLTMIST cards, so we can view how well the approximated gaffs match the tabulated gaffs. And then lastly, subcase 3 is the state space approach. So in our MINSTAT card, IT max is 100, and we've also increased the number of lags up to 10. Because usually in order to achieve the same level of RFA accuracy, the number of aerodynamic lag routes used by the modified minimum state method should be more than that of the Rogers method. So now we'll compare the RFA results. So both Rogers method using 5 aerodynamic lag routes and the modified minimum state method using 10 aerodynamic lag routes compares well with the tabulated QHH. So our computed values here are black, Rogers is red, and then the modified minimum state is green, and you can see that they all pretty much lie on top of each other. So on the upper left we have QHH of 1,1, We have QHH12. On the bottom left, we have QHH21. And then on the bottom right, we have QHH22. And so the multiple discrete values here are the different reduced frequency values. Next, we'll compare the flutter solution. So on the left, we have the frequency domain approach. And there's two ways you can compare how well your approximation is. One, you can just look at the flutter results, which are shown tabulated here. And then also you can look at the VGF diagrams. This is just the VG diagram to see how well the damping values match, even not just the flutter crossings, but everywhere. And you can see that the state space approach using Rogers and state space using modified minimum state method, the VG diagram matches very well with that of the frequency domain approach. So we have a very good approximation. And if we look at the actual flutter results, the flutter dynamic pressure in PSI is practically identical, and then the flutter frequency also is practically identical for all three approaches. So we have a very good approximation defined. And that concludes section 3.